Let's work on example 1.7, where we have continuous varying density object happening in one dimension, and we want to find the center of mass. So let's draw a picture. We have a 3-meter long rod, and let's establish our Cartesian plane or our coordinate system like that. Remember, it doesn't matter how you start it. You could have put the y-axis on the right edge. Everything's going to make sense as long as you're consistent. But let's imagine that I have the left edge at 0, the right edge is at 3, and our density function starts at 6 kilograms per meter. On the left edge, again, it doesn't matter where I put it, but on one edge it's 6, and on another edge it's 3 kilograms per meter, and I know that it decays linearly. So here we actually have to come up with the density function, and after some thinking about it, the density function should be 6 minus x. You can think of that as if x is equal to 0, you're over here on the left, and you get 6 minus 0 is 6, and if you're on the right-hand side, x is equal to 3, and 6 minus 3 is 3, and that's your density over there. So that is our linearly decaying density straight line function. So let's work on computing the mass, because remember, to find the x position, or the position of a center of mass, we need to find a moment divided by total mass. So let's work on total mass by integrating the density function. So we will integrate between 0 and 3. Six minus x. Finding an antiderivative and evaluating between the two boundary points tells us that the mass is 27 over 2, or 13.5. Now let's find the moment, the numerator for the position. We always find moments by integrating positions times densities. So we will integrate between 0 and 3 the position of x multiplied by the density function 6 minus x with respect to x, and after distributing we would have a 6x, which would integrate to a 3x squared, and a minus x squared, which would integrate to a minus 1/3 x cubed, and by the fundamental theorem of calculus we will run that between the two boundary points and take the difference. If we do this, we find a moment of 18. Ooh, let's throw some units on this. The total mass would be kilograms, because we integrated all of the kilogram per meters with respect to the meters, and the moment would be kilogram times meters. So putting the pieces of the puzzle together, we have the position given by a moment divided by mass, the moment being 18 kilogram meters, the mass being 27 over 2, or 13.5 kilograms. We see that kilograms cancel, and we are left with meters, which makes sense because it is a position variable. And the center of mass, the position where we should hold the object, is at 4/3, or 1 and 3 repeating. So let's go back to our picture. Halfway would be 1.5, so 1.3 would be somewhere right there. That's where we should hold the object in order to make this continually varying density function, which gets lighter as you move to the right, perfectly balanced.